For centuries, human imagination has been captivated by the question of whether we are alone in the universe. We've dreamed about what life might look like on distant worlds and wondered about the civilizations that could exist beyond our sight. Now, with the James Webb Space Telescope, JWST, the most powerful telescope humanity has ever built, we may finally begin answering this age-old question. This revolutionary telescope, launched to explore the distant reaches of space and the nature of exoplanets, is already delivering groundbreaking observations. One of its primary targets is the closest star system to our own, Proxima Centauri, located just over 4 light-years away. As scientists study this neighboring system, they have observed unusual signals from one of its planets, Proxima Centauri B. These signals, interpreted as artificial lights, have sparked intense curiosity and speculation among astronomers. But what do these lights mean? Could they be evidence of intelligent life on Proxima B? Let's explore the remarkable findings of the JWST and their potential to change our understanding of life in the cosmos. The only confirmed life we know of exists on Earth. Since the dawn of civilization, we have questioned whether life might also exist elsewhere in the universe. In our quest to find the answer, astronomers Jill Tarter and Thomas Pearson initiated the search for extraterrestrial intelligence, SETI, in 1984. SETI's mission was to detect signs of intelligent life by listening for radio signals from distant star systems. Radio waves can travel vast distances through space with minimal loss, making them one of the most effective ways to detect life beyond Earth. To this end, SETI employs an array of 42 radio telescopes known as the Allen Telescope Array in the Cascade Mountains of California. This network of telescopes is specifically designed to capture potential extraterrestrial radio signals. However, despite over 3 decades of searching, no conclusive alien signals have been found. In the meantime, humanity's technological capabilities have made leaps and bounds, culminating in the successful launch of the James Webb Space Telescope. Positioned nearly 1 million miles from Earth, JWST is equipped with state-of-the-art, highly sensitive instruments that allow it to study the atmospheres of exoplanets, planets orbiting stars beyond our solar system. With the JWST, scientists can now look farther and with greater clarity than ever before. 20 years ago, exoplanets were a mystery. We knew of none outside our solar system, but today, we have identified more than 4,000 exoplanets orbiting distant stars. Scientists believe that trillions more may exist throughout the universe. One way we might detect life beyond Earth is by observing plant life on other worlds. When the Galileo spacecraft journeyed to Jupiter, it briefly turned its instruments back toward Earth and detected a vegetation red edge, VRE, signature, a unique reflection of red and infrared light emitted by plant chlorophyll. This VRE biosignature was definitive evidence of vegetation on Earth. If a planet were covered in forests or jungle similar to Earth, it might also produce a VRE signal detectable from afar. The JWST's sensitive instruments can measure the VRE of Earth-like planets orbiting in habitable zones, the regions around stars where temperatures might allow for liquid water on planetary surfaces. When an exoplanet passes in front of its star, JWST can capture and analyze the starlight passing through the planet's atmosphere, identifying missing wavelengths that reveal specific atoms and molecules. Each element has a distinct fingerprint in the form of wavelengths it absorbs, allowing scientists to determine the atmospheric composition and assess the possibility of life. For instance, an Earth-sized planet with an atmosphere containing oxygen, nitrogen, and carbon dioxide might indicate conditions that could support life. But the JWST is also capable of identifying technological life. If we observed a planet with a high concentration of chlorofluorocarbons, CFCs, chemical compounds produced by human industry for uses such as refrigeration and cleaning, it would be a clear indicator of advanced civilization from light years away. Extraterrestrial observers monitoring Earth could detect our own CFCs, signaling our technological presence. If the JWST were to discover CFCs in an exoplanet's atmosphere, it would be a groundbreaking sign of intelligent life. Life on other planets, however, might not look anything like life on Earth. Earth hosts extremophiles, organisms, primarily bacteria, that thrive in environments considered uninhabitable to most forms of life. Some extremophiles can withstand temperatures as high as 250 degrees Fahrenheit, while others can survive in acidic environments with a pH below 3 or endure sub-zero temperatures. Many extremophiles inhabit places on Earth where one might not expect life at all, such as deep-sea hydrothermal vents or acidic lakes. While it's possible that life on exoplanets might also adapt to harsh conditions, Earth-like planets, those with moderate temperatures and liquid water, are thought to have the best chances of hosting life. Such planets are likely to be found orbiting stable stars that provide the necessary conditions for life to evolve. The JWST's first major mission will focus on the TRAPPIST-1 system, located 40 light-years from Earth. TRAPPIST-1 is a red dwarf star orbited by 7 Earth-sized rocky planets. 3 of these planets are in the star's habitable zone and might have liquid water on their surfaces. Despite TRAPPIST-1's relatively cool and small stature compared to our Sun, the close orbits of its planets could produce Earth-like conditions. But our nearest neighboring star system, Proxima Centauri, offers the best chance of detecting artificial lights outside our solar system. Proxima Centauri is a red dwarf star that emits only a fraction of the Sun's light, and for Proxima Centauri B to sustain liquid water, it must orbit much closer to its star than Earth does to the Sun discovered in 2016. Proxima B is a rocky planet with a mass similar to Earth's. It lies in Proxima Centauri's Goldilocks zone, where conditions might support liquid water. However, its proximity to its star presents challenges. Red dwarfs are known for emitting strong solar flares and high-energy radiation that could erode a nearby planet's atmosphere, especially if the planet lacks a protective magnetic field. Nevertheless, Proxima B's orbit is close enough to receive sufficient light for Earth-like temperatures, provided it has an atmosphere to retain heat. Due to its close orbit, Proxima B is likely tidally locked, meaning one side of the planet perpetually faces its star, resulting in a hot day side and a frigid night side. This unique configuration could potentially enable an advanced civilization on Proxima B to install solar panels on the day side to generate energy, which could then be used to light up the cold, dark night side, producing a detectable artificial illumination that the JWST could observe. One of the most significant questions concerning Proxima B is whether it has an atmosphere capable of supporting life. To determine this, scientists need to measure the planet's density and composition by observing it during transits across its star. When a planet transits, starlight passing through its atmosphere reveals key atmospheric components such as oxygen, water vapor, and methane, which could signal the presence of life. However, the odds of Proxima B's orbit aligning for visible transits are only about 1.5%. Even without direct transits, the JWST can study the planet's infrared radiation. A rocky planet emits heat differently from a star, and the JWST was specifically designed to capture infrared light. By comparing the infrared emissions from Proxima B's day side and night side, scientists can infer the presence of an atmosphere. If the temperature difference between the two sides is moderate, an atmosphere is likely helping distribute heat across the planet. In the future, scientists hope to conduct more comprehensive analyses of Proxima B's atmosphere. If elements like oxygen, water vapor, and methane are detected, they may suggest habitable conditions or even active life. However, capturing these atmospheric details is challenging. Scientists must carefully analyze light as it reflects off or passes through the atmosphere. Though JWST was not explicitly designed to search for extraterrestrial life, it offers insights into the atmospheres of some of the closest potentially habitable exoplanets. To achieve a more thorough investigation, astronomers are developing ground-based observatories like the Extremely Large Telescope, which will begin operation in the 2020s and is equipped to analyze exoplanet atmospheres in greater detail. Meanwhile, JWST observations may include elements like ozone, which is also indicative of life. In the coming years, new telescopes may further enhance our search by employing advanced technologies to block out the overwhelming light of a host star, allowing us to study the starlight reflected from planets more easily. While the search for life is filled with challenges and the potential for false positives, JWST represents a transformative step. The gases that we associate with life, like methane and oxygen, can also arise from non-biological processes, which means astronomers must be careful in their interpretations. The primary goal of JWST is to understand the formation of galaxies, stars, and planets, and to investigate the atmospheres of exoplanets in their stars' habitable zones. Although its mission spans a vast array of scientific goals, a major focus is the search for biosignatures and technosignatures, clues that could indicate life or intelligent civilizations. The JWST's infrared instruments can detect light signatures even from distant planets shrouded in darkness. Many planets, particularly those in the habitable zones of their stars, have atmospheres that the JWST can analyze for specific chemicals associated with biological processes. For example, oxygen and methane are frequently produced by life forms, and if present together might be signs of life. Observing an abundance of either gas in an exoplanet atmosphere would provide a strong indication of potential habitability. Additionally, the JWST can pick up on other signals, such as the presence of industrial pollutants or artificial lights, which may signify an advanced civilization. Unlike previous telescopes, JWST's instruments are tailored to capture and analyze the faint glow of exoplanets orbiting distant stars. One approach used to study exoplanet atmospheres is transit spectroscopy, which occurs when an exoplanet passes directly in front of its host star from our viewpoint. During this event, the JWST can measure the starlight passing through the planet's atmosphere, revealing a spectrum filled with clues about its composition. Each element and molecule within the atmosphere absorbs light at specific wavelengths, creating a unique spectral fingerprint that astronomers can decode. By comparing these fingerprints, scientists can identify elements like carbon dioxide, methane, and water vapor, indicators of potentially habitable conditions. One intriguing target for the JWST is Proxima Centauri, the closest star system to our own, located only 4.24 light-years away. Proxima Centauri hosts an exoplanet, Proxima B, which lies within its habitable zone. Discovered in 2016, Proxima B has garnered interest due to its Earth-like size and potential for liquid water. Despite its proximity to Proxima Centauri, Proxima B faces several challenges that may hinder its ability to support life. It is likely tidally locked, meaning that one side permanently faces its star, resulting in extreme temperature differences between its day and night sides. Red dwarf stars like Proxima Centauri are also notorious for frequent and intense solar flares, which may strip away planetary atmospheres, exposing surfaces to harmful radiation. For Proxima B to maintain an atmosphere, it would need a strong magnetic field to shield against these solar eruptions. Despite these challenges, Proxima B remains a prime candidate for further observation due to its proximity and location in the habitable zone. Recent observations of Proxima B have detected what could be artificial lights, suggesting the potential presence of intelligent life. If an advanced civilization exists on Proxima B, it might compensate for the planet's harsh environment by generating artificial light to illuminate the dark side. In this case, JWST could detect these lights through subtle changes in the planet's luminosity as it orbits its star. The possibility of detecting technosignatures, such as artificial lights, represents a new frontier in the search for extraterrestrial intelligence. SETI traditionally has focused on radio signals, hoping to intercept communications between extraterrestrial civilizations. However, artificial lights on the dark side of an exoplanet might offer a more tangible form of evidence, revealing the presence of cities, infrastructure, or even solar energy networks. Detecting a civilization's artificial light would be an unmistakable sign of advanced technology. Beyond Proxima Centauri, the JWST is set to study the TRAPPIST-1 system, a star system only 40 light-years away. TRAPPIST-1 is a red dwarf star surrounded by 7 rocky, Earth-sized planets. 3 of these planets are located in the habitable zone, where liquid water could exist. This discovery has ignited excitement in the scientific community, as the chances of one of these planets harboring life are notably high. The TRAPPIST-1 system is intriguing not only because of the number of planets, but also because of their close orbits. Although the system star is smaller and cooler than our Sun, the close proximity of its planets allows for Earth-like conditions. The JWST aims to examine the atmospheres of these planets for any signs of life or biosignatures, including gases like oxygen and methane. The field of exoplanet exploration has advanced considerably since the early days of planet hunting. The first exoplanet discovered around a sun-like star, 51 Pegasi b, was found in 1995. This discovery confirmed that planets orbit other stars, sparking a revolution in astronomy. Today, over 5,000 exoplanets have been cataloged, and each new discovery reveals more about the diversity of planetary systems. Many of these exoplanets reside in the habitable zones of their stars, regions where temperatures allow for liquid water. The discovery of Earth-like planets in these zones has bolstered the possibility that life might exist elsewhere. Yet, the presence of liquid water alone does not guarantee life. Other factors, such as a stable climate, protective magnetic fields, and chemical ingredients, are essential for sustaining life. JWST observations could provide crucial insights into these conditions, further narrowing the search for habitable worlds. Life, as we understand it, requires water. Water is a solvent that facilitates the complex chemical reactions needed for life to develop and sustain itself. However, life on Earth also demonstrates remarkable adaptability, thriving in environments that might seem hostile to most organisms. For instance, extremophiles, organisms capable of surviving in extreme conditions, have been found deep within Earth's crust, in acidic lakes, and even near hydrothermal vents on the ocean floor. These organisms provide a model for the kind of life that could exist on distant, seemingly uninhabitable planets. Some exoplanets may experience extreme temperatures or high levels of radiation, yet extremophiles on Earth suggest that life could exist in environments once thought too harsh to support it. As astronomers continue to push the boundaries of what is possible in the search for extraterrestrial life, the James Webb Space Telescope, JWST, has become a pivotal tool in our quest to uncover whether we are alone in the universe. In addition to its ability to study exoplanet atmospheres, JWST is equipped to observe a range of celestial phenomena that could offer new insights into the conditions that foster life beyond Earth. For example, by studying distant galaxies and star-forming regions, JWST can help scientists understand how planetary systems, including those that might harbor life, evolve over time. One of the most promising aspects of the JWST is its ability to observe the early universe in unprecedented detail. As light travels across space, it takes time to reach us, meaning that by observing distant objects, we are effectively looking back in time. JWST's infrared capabilities allow it to peer through cosmic dust and observe the formation of the first galaxies and stars, objects that are billions of years old. Understanding how these early cosmic structures formed could provide crucial context for our own solar system's formation and offer clues about the conditions necessary for life to emerge. Another fascinating feature of JWST's design is its ability to detect chemical signatures of life beyond just the typical biosignatures we associate with Earth. In addition to oxygen, methane, and carbon dioxide, JWST can detect other molecules that may be indicative of alien biochemistry. For example, sulfur compounds could suggest the presence of life forms that rely on a different metabolic process than those on Earth, such as sulfur-based life that thrives near underwater volcanic vents. The ability to detect a broader range of chemical signatures increases the likelihood of finding life forms that are vastly different from anything we can imagine, potentially expanding the very definition of life itself. Furthermore, JWST's ability to study the formation and evolution of planetary systems gives astronomers the tools to assess the likelihood that other stars could host habitable planets. By observing the conditions in young star systems, scientists can determine the prevalence of water-rich planets and assess how often these planets develop atmospheres that could support life. This information could help narrow down the search for exoplanets that are most likely to harbor life, especially in the regions of space where habitable conditions are more common. While the hunt for extraterrestrial life is still in its early stages, the advancements brought about by the JWST are already reshaping our understanding of the cosmos. If artificial lights or other signs of intelligent civilizations are detected on distant exoplanets, it would not only be a monumental discovery in the field of astronomy, but would also challenge our view of life itself. The implications of finding intelligent life elsewhere are profound, touching on philosophical, ethical, and even existential questions about humanity's place in the universe. Whether we find microbial life on distant planets or confirm the existence of extraterrestrial intelligence, The discoveries that emerge from the JWST's observations will likely shape our understanding of life in the cosmos for generations to come.